So now take it away, Professor Katerina.
It's already. Sorry for the inconvenience. Good morning, good afternoon, good evening to all colleagues, students, participants of Geoenvironmental Engineering webinar. I'm Professor Katerina Donevska, and my today's presentation is about landfill site selection methodologies and criteria. The presentation is consisted of three parts. The first one is the background. The second one is a review of landfill site selection methodologies and criteria, which is based on a recently published research into the Journal of Indian Institute of Science in the special edition on the landfills. And I would like to take this opportunity and thank the guest editor of the journal, Professor Krishna Revi, for inviting me to contribute to this special edition of landfills. This paper was prepared together with my PhD student Jože Jovanovski and Master of Science student Ljubčer Ligorova. The third part is about a case study for regional non-hazardous landfill site selection for a part of my country in the Polog region in North Macedonia. It is based on a nearly 10-decade research that was performed together with Associate Professor Pece Gorševski from Bowling Green State University and Professors Milorad Jovanovski and Associate Professor Igor Peševski, both from the Faculty of Civil Engineering in Skopje. The research was performed during my Fulbright grant at Bowling Green State University. I will start my presentation with a little history with waste management disposal practices. As we are all familiar with, waste management practices were at the beginning dumping procedures associated with many environmental problems like smoke, odor, contamination of surface waters. However, leachate that was not collected contributed to contamination of groundwater and also emissions of landfill gases into the atmosphere. Contemporary engineering facilities were created to minimize the environmental impacts from the dumps, and they are well engineered, that are landfills that are well designed, well engineered, well operated landfills for disposal of solid waste. These facilities have been, although they are at the bottom of the hierarchy of the integrated municipal solid waste practices, they are most commonly used method for disposal of municipal solid waste worldwide. I will present some data about sustainable municipal waste treatment practices for the European Union as an aggregate country of 27 countries for the time period between 1995 and 2019. On the picture, the data are presented for 5 waste management treatment alternatives like material recycling, landfilling, incineration, composting, and other techniques. From the data, it can be indicated that the quantities of the municipal solid waste from 1995 to 2019 have been reduced twice. In the contrast, the waste management quantities that have been recycled, incinerated, composted, they have been doubled in the same time period. When it comes to spatial distribution of the waste management practices within the countries members of the European Union, the figures indicate that the Scandinavian countries and Central European countries, they have the highest rates of the municipal solid waste that has been incinerated in 2019, in the year 2019. The same applies also to the waste management, to the waste quantities that have been recycled. However, the next picture presents data about waste management, about waste quantities that have been disposed on landfills in 2019. It can be clearly seen that also Scandinavian countries, Germany and other Central European countries dispose the waste quantities in the range from 0 to 6 kilograms per capita in 2019, which is really astonishing data that they are nearly zero waste alternatives. However, even such sustainable waste management practices are being implemented decades ago. There are still many landfills operating within the European Union territory. This map presents especially the regions with dark blue, represents regions where the number of modern landfills that are currently operating are above 35 landfills. However, although there are many still operating landfills, there will be a need for new landfills in the future. Siting a new landfill is the most crucial task in the process of planning of new landfills. And this process of planning and processes of landfill siting are always regulated by national regulations or maybe federal or local regulations. For example, within the European Union, the directive from the landfill of waste, especially the Annex 1 for general requirements of all classes of landfills, and within the United States, the 40 Code of Federal Regulation 258, the criteria for municipal solid waste landfill, they enforced strict regulation regarding the phase of planning or restrictions of the locations of the landfill, during the phase of design of the landfills and phases of operations and post-closure of the landfills. Generally, landfill site selection process is accepted to be consisted of 4 phases. The first phase includes identification of all the areas that should be excluded from further consideration as potential landfill sites. To exclude all these areas that are not suitable for landfill, some type of criteria are used that are called constraints or exclusionary criteria. These constraints or exclusionary criteria involve legal restrictions on landfill siting or some physical constraints. When the areas are being excluded, then the second phase includes a preliminary assessment of all the remaining potentially suitable areas. This phase is associated of implementation of some specific methodology, for example, the GIS or multi-criteria decision analysis or compromising programming or some other multi-criteria decision analysis methods, and inclusion of non-exclusionary criteria to rank the potentially suitable areas. Afterwards, a short list of sites has been listed, and this short list of sites needs detailed investigation of the local conditions in the area. For example, the bedrock type, the hydrogeology, maybe the climate of the region. And after that, a preliminary engineering design is performed, an environmental impact assessment study, which compares some landfill costs. At the end, it ends with the selection of the most preferred site. The selected site, then the final planning of the site is performed, also designer's procedures, and also environmental impact assessment licensing. The most important question in the preliminary assessment process is which method to apply. Should we apply the GIS? Should we apply the multi-criteria decision analysis? Should we apply maybe the ordered weighted average or analytical hierarchy process, analytical networking process? To answer that question, a review of the most relevant scientific papers has been performed within the electronic databases of peer-reviewed scientific journal papers, like that were published into the American Society of Civil Engineering Library, into the Elsevier, into Springer, Sage journals, and Taylor and Francis. Afterwards, Google Scholar browser was extensively searched for additional papers and also for the citations of all these papers. The timing of the research was from July to September 2020, and there was no filter on the year of publications of the journal papers. The terms that were used that were landfill site selection, landfill siting, and landfill allocating. All the list was then selected to be all the papers in English language, and it resulted with the final list of 89 scientific papers. Statistical analysis of all these 89 papers indicated that there are 30 case study countries have been identified. Among them, the top 5 are the Iran, Turkey, India, Greece, and the USA. All of they represent nearly 57% of the total articles. Regarding the time of temporal distribution of these research articles, it can be indicated from this temporal distribution that the most frequently publication occurred from 2012 to 2019. And this figure presents the total number of publication, the temporal distribution of total number of publication, and also the number of publication using the GIS method. It's very useful to see that many of the researchers use the GIS as a method, as a tool in their decision analysis. Nearly 86% of the researchers use GIS. GIS has been widely used due to the fact that enables spatial decision analysis, and the site selection is also a spatial problem. That's why GIS is been widely used. Regarding the GIS, the geographical data model that has been used, GIS raster model is prevailing over GIS vector analysis. Also, GIS analyses have been also combined with many multi-criteria decision analysis to select the most suitable landfill sites. For example, GIS has been always used to prepare the geospatial database, while MCDA, some of the MCDA techniques has been used to rank all alternatives, or maybe to assign weights to some of the criteria. Among the methods that have been mostly most popular is the weighted linear combination. Weighted linear combination is most frequently used, and it's a very simple method to use. It's mainly used for ranking the alternatives. And this method allows adding weights to each criteria, where the sum of the weights should be constrained to 1. This adding weights to criteria enables making a list of priority criteria and rating the criteria according to their priority. Also, these weights enable some trade-off level where high criteria weights can compensate for low criteria scores. Estimation of the weights can be in weighted linear combination can be on the base of equal weighting, on the base of ratio scale weighting, and also analytical hierarchy processes. Equal weighting happens when the decision maker makes a consideration that all the criteria have the same meaning, same level of significance, and they're all assigned equal weights. Well, ratio scale weighting is when all the information are being normalized, and analytical hierarchy process is being widely used by the researchers, mainly for criteria weighting. It has been less frequently used for ranking the alternatives. Analytical hierarchy processes in assigning weights is using pairwise comparison matrix. This pairwise comparison matrix enables comparison of each pair of criteria. Comparing the criteria is very important to understand which criteria is more important and how much more important. That is enabled by scaling the importance of the criteria in the scale from 1 nint in the scale of less important to the 9 as more important. The criteria can be also scaled with 1, which means equally importance. Another methods that have been widely used and that are very interesting is the combination of remote sensing with GIS methods and also with some MCDA for ranking of the alternatives. For example, remote sensing and GIS are being used for preparing of geospatial database, where remote sensing is used for preparing the vegetational index database, or maybe it can be used for land use, preparing of land use database. because it enables getting data from the satellite, and it also enables the decision maker to make the decision upon regularly updated real-time data. The same combination, some authors practice the same combination, for example, the combination of GIS analytical hierarchy processes with Drastic, where Drastic as a software tool is used for assessment of groundwater vulnerability to contamination of some existing landfill sites, and preparing the geospatial database together with GIS and analytical hierarchy processes for use for ranking the alternatives. When it comes to the criteria, the research identified two groups of criteria. The first group, and let's say the more important group, are the constraints that are the criteria that are being used to exclude some area as potential area for landfill siting. And the other group of criteria are non-exclusionary criteria. Within the constraints or exclusionary criteria, they can be legal, like for example, the distance to airports, distance to falls, distance to surface water bodies, for example, the distance from the boundary of the landfill to the river or the lake, then the distance to boundary of the residential and recreational areas, distance to sanitary protection zones and around public water supply, distance to cultural heritage, and depth to groundwater. For example, in our national regulation, the depth from the bottom of the landfill to the groundwater table is also strictly regulated. The other group in the group of constraints or exclusionary criteria are physical constraints that are areas that cannot physically be used as landfill sites, for example, because they are areas with surface waters or maybe railroads or maybe motorways, national parks, and lands with urban and rural settlements. Non-exclusionary criteria, many authors use two-level hierarchy. For example, they group all the criteria in two groups. The first group are the main group criteria, and all these non-main criteria that are in the main group of criteria are grouped to fulfill some aim. For example, the fulfilling an environmental aim or fulfilling some economical aim. And the other group are sub-criteria. And these sub-criteria are listed according to the local conditions that fulfill the environmental consideration or economical consideration or aim. Some authors, however, use only one level hierarchy of non-exclusionary criteria. They only list only the relevant criteria for the local conditions. When it comes to non-exclusionary criteria, the result of the research indicated that the most popular main criteria are environmental, economic, social, hydrogeological, and topographical and morphological criteria. Well, the 20 most used sub-criteria are distance to surface water, distance to urban area, distance to road, and many other criteria. It's important to notice that the criteria might be not easily measurable. Well, maybe some of the criteria might not be measured in the same scale. Also, it is sometimes that an expert knowledge is being used to assess the data of some criteria. Using an expert knowledge might contribute to some degree of uncertainty. That's why a need for criteria standardization is required. And for criteria standardization, usually fuzzy set is used, fuzzy set theory is used. And to use the fuzzy set theory, we need to specify a fuzzy membership function. Fuzzy membership function and is the type of the fuzzy membership function should be specified, and also the control points of the fuzzy membership functions. There are two control points, the control point 0, which means non-full membership or excluding all the areas having values 0 as not suitable, and fuzzy membership function 1, meaning full membership or including all the areas as suitable for landfill siting. Usually, selection of the type of the fuzzy function and the control points is done by using expert knowledge. Using these fuzzy membership functions, criteria are being standardized, and standardized maps are then used into the detailed assessment. Now we come to the regional, to the third part, to the regional non-hazardous landfill site selection by using integrated fuzzy logic, analytical hierarchy process, and geographic information system for the region Polok in North Macedonia. The location of the region is in the northwestern part of Macedonia, and its relief is mainly consisted of lowland valley, surrounded by high mountains on the west and on the southeast and on the east. There is a national park on the west of the region, and there is another national park on the east of the region. In the eastern part of the region, there is a significant spring that supplies with water the country's capital. Regarding the current municipal waste management practices, they are not, they include only dumping of the municipal solid waste, and they are associated with many environmental problems. So there is a clear need to construct and plan a new landfill. The catchment area is consisted of two main cities and nearly 140 settlements that are located into 17 municipalities. The total number of population is nearly 300,000 citizens. And the estimated landfill capacity is assessed on 4,400,000 cubic meters, including daily and final cover material. Here are some pictures of the terrain. These are the mountains, pictures from the mountains, high mountains on the west, and this is a view from the mountain on the east towards the valley. And on the picture, we can see a sharp border between the flat valley and the high mountains. The catchment, regarding the geology, on the western part, there are Paleozoic metamorphic complexes as dominant units. On the lowlands, the geology is represented by sedimentary highly permeable rock masses. On the southeast, the mountain is consisted of carbonate complexes. It is the same with the mountain on the east, but however, there are also occurrences of karsts. There are carbonate complexes, but very often occurrences of karsts. There is also an active fault that passes through the area and passes also through the region. Regarding the hydrogeology, the lowland is consisted of very extensive, high productive aquifer. And the mountains on the west, they present very low, they have low productivity of aquifers. And the mountains on the southeast and on the east are also high productive aquifers. On the eastern mountain, there is a spring, the spring Prasche in the karstified terrain. The spring is with capacity from 3.3 cubic meters per second to 7.5 cubic meters per second. And it supplies with drinking water the capital of the country, Skopje. The water is of good quality. It enables water supply by gravitation. That's why the spring is of very high significance. And that's why the spring is under protection with national legislation. There are 3 protection zones around the spring. The first zone is around the spring. The second zone is the mountain, karstified mountain in the eastern part. And the third protection zone is the lowland, the valley, the high productive aquifer. So the nearly whole territory in the lowlands belongs to the protection zone of the spring. When the criteria have been defined for selection of the landfill, the landfill directive has been taken into consideration, and all the requirements in the landfill directive have been taken translated into some criteria. For example, in criteria selection, 9 environmental criteria have been selected and 3 criteria into economic group of criteria. Afterwards, the criteria have been standardized using fuzzy membership functions and control points, and expert knowledge has been used for selection of the fuzzy membership function and their control points, and criteria maps have been created. Afterwards, weights were assigned only to the environmental group of criteria using analytical hierarchy process, and economic criteria were equally weighted. Weighted linear combination as a method was used to aggregate the criteria, both the environmental criteria into an intermediate suitability map and also economic criteria into another intermediate suitability map. After that, all scenarios for final aggregation of intermediate suitability maps were defined and final suitability maps were created. The criteria, the methodology, first included a definition of constraints and excluding all the areas that should be, that there are some legal requirements and physical constraints. That are the national parks on the east and west, the protected zone around Spring Rašče, also urban and rural areas and some lakes. Then the criteria, non-exclusionary criteria were, as we said, grouped in 2 groups into the main criteria that are aiming some environmental aim, protection the environment, and then a group of economic criteria and the sub-criteria or factors in the group of sub-criteria or factors in the group of environmental criteria that were slope, elevation, distance from rivers, distance from lakes, distance from springs, land use, hydrogeology, distance from faults, and distance from urban and rural areas. The group of economic criteria consisted of 3 criteria: proximity to roads, proximity to building materials, and proximity to dense population. The next phase was to define the fuzzy membership functions and their control points. For the environmental group of criteria, the slope is considered as important factor because steep slopes, for example, slopes over 30%, may contribute to excess surface runoff and therefore propagation of contamination around the landfill. And also slopes of over 30% are being considered as not suitable for landfill siting, while slopes below 11 degrees are 11% are being considered as suitable for landfill siting. Also, slopes are considered, steep slopes are considered as not suitable due to the high excavation costs. When we have high slopes, we have high excavation costs. Regarding elevation, it was considered that high elevations, for example, elevations above 11 meters above sea level, might lead to high precipitation and maybe some freezing temperatures during winters due to the climate conditions of the region. And that's why all the areas above 1,000 meters above sea level were assigned values 0 or on the fuzzy membership function, or they were excluded as potential landfill sites. Areas that belong to elevation below 800 meters above sea level are considered as suitable for landfill siting. For the elevation, G-shaped decreasing fuzzy membership function has been used for the sites, for the areas between 800 and 1,000 meters above sea level. The same applies for the criteria distance from rivers, where 3 classes of rivers have been estimated, and also to the distance from lakes and distance from springs criteria. For example, for distance from rivers first class of rivers, 500 meters is been set as a constraint So all the areas that fall within the distance 0 to 500 meters have been excluded from further consideration. That is the control point 0 on the fuzzy membership function, while the control point 1 or suitable areas are the areas that are on a distance more than 800 meters. The fuzzy membership function that was accepted, it is sigmoidal increasing. Regarding the same applies to all the other criteria like distance from lakes, distance from springs, distance from falls, and distance from urban areas. When it comes to hydrogeology, discrete values for the hydrogeology have been assigned, for having in mind that the whole region falls within the protection zones of the spring, and having in mind the requirements of the directive on the landfill of waste, and especially on the annex that's requiring special conditions about the landfill siting, the highest values or most suitable areas for landfill siting are considered some impermeable formations without aquifers. They have been assigned the highest values, while the lowest values, so the lowest suitability for landfill location, are assigned to high to medium transmissivity and permeability soils, for example, the soils that are in the lowlands. Land use has been considered as a significant environmental condition because there are national regulations that prohibit landfill siting on several agricultural land. For example, it forbids siting on landfills on agricultural first-class land. That's why also discrete values were assigned to this land use. For example, the forest has been assigned the highest value, while at the agricultural land has been assigned the lowest value, meaning least suitable area. Regarding economic factors, proximity to road means what are the expenses that are required to construct, for example, new roads for the new site, for the construction of the new site. And we always want to minimize the cost for new constructions. And that's why the criteria is set to minimize the distance between the landfill and the current settlements. That's let's say a little bit, it's opposite criteria compared from the distance from urban areas criteria, because it tends to minimize the distance from the potential landfill site and settlements. Proximity to building materials is set as a criteria to minimize the costs for materials that are required for construction of the base of the impermeable base of the landfill, and also the costs that are required for daily and final cover material during landfill operation. And proximity to dense population is set as a criteria because it sets the operation costs for the landfill. And also the control points for all these criteria are being set, and also the types of the membership function. Using this criteria, the criteria maps are being created for both the environmental group of criteria and also for the economic group of criteria. For the environmental, the first map presents the hydrogeology standardized map. The second one, distance from faults. This one presents elevation. This one presents land use criteria map. This one, distance from rivers. This one, distance from lakes. Distance from spring map. Distance from urban areas. And the last of the group of economic factors is slope. The last three maps include proximity to road criteria, proximity to building materials, and proximity to dense population. Weights were assigned only to the environmental set of criteria, and weights were estimated using analytical hierarchy process, the pairwise comparison matrix. And from the matrix, we can see that the higher weights, according to the expert knowledge, was assigned to the hydrogeology, which is expected due to the weighting of the criteria and to the importance of the hydrogeology for the particular local conditions. Having these weights, then they are added to each criteria map, and using weighted linear combination, 2 intermediate maps were constructed. One intermediate map for the economic set of criteria and other intermediate map for the economic set of criteria. Afterwards, 3 scenarios were defined for integrating these 2 intermediate maps into final suitability maps. The 3 scenarios include: the first scenario is when higher weights are assigned to the environmental group of criteria and lower values of the weights are assigned to the economic group of criteria. The second scenario includes assigning equal weights both to the economic and to the environmental group of criteria. And the third scenario includes assigning a lower value of the weight coefficient for the environmental group of criteria and higher value for the economic group of criteria. For these 3 scenarios, 3 final suitability maps were created that are presented on these 3 figures. The red areas on the figures are presenting areas that are suitable for landfill siting, meaning that the fuzzy membership numbers have value between 0.8 and 1. It can be clearly indicated from the distribution of the red areas in three figures that in the first figure, when we are assigning higher values for the environmental set of criteria, the red areas are in the higher elevations. While when we are assigning equal weights to the both group of criteria, the suitable areas or the red areas are going a little bit more on the lower elevation, while for the third scenario, the red areas or the most suitable areas lie in the lowland. This is a very important conclusion because the aim of the paper was to indicate the flexibility of the methodology and the importance of the assigning weights both to the environmental and both to the economical group of criteria. That's very important because future generation and future researchers and decision makers should be aware of the flexibility of each methodology and should be aware of the importance of weight selection when they make their decisions. So at the end, I would like to conclude that we should all think globally, but act locally. Thank you.